In this video, we're going to talk about how to graph exponential functions. Looking at the first problem, it reads, the graph of f of x equal to negative 1/3 times 1/2 raised to the power x minus 5 all plus 6 is shifted downward 6 units and then shifted left 5 units, stretched vertically by a factor of 6, and then reflected about the x-axis. What is the equation of the new function g of x? What is the y-intercept, what is the domain, and what is the range? Let's pick apart each piece first of all. The first thing that we need to think about is how it is being shifted. Since in our particular problem, it's shifted down 6 units, that refers to something happening outside or after the power is being done. So the first thing that's going to happen is we're going to have the negative 1/3 times the 1/2 raised to the x minus 5 all plus 6. You're going to subtract 6. In other words, this part is going to become a 0. And this is going to lead to the new equation of negative 1/3 to the 1/2 all raised to the x minus 5. This just reflects the first thing, which is a downward shift of 6 units. Now let's shift it left 5 units. Shifting left or right affects x, and x is in the power, so this has to be in the power too. A shift left is opposite to what you think it would do. Instead of subtracting 5 on the inside of the operation, it adds 5. So now what we're going to have is this problem is going to be transformed and changed again into negative 1/3 times 1/2 to the x minus 5 plus a 5. Now the minus 5 plus 5 is going to give us a 0, and that means that this transformed relationship is going to be negative 1/3 times 1/2 raised to the x. That reflects both the shift downward 6 units and the shift left 5. Our next thing is a vertical stretch by a factor of 6. Vertical affects y, so this happens outside of the main operation. The main operation is the exponential function, so it's got to happen outside of that. A stretch or a compression is a multiplication by a factor. Since this one is being multiplied by a factor of 6, it basically means we have 6 times the negative 1/3 all multiplied by 1/2 raised to the x. That is going to lead us now to the equation negative 2 times 1/2 raised to the x. Don't make the mistake of thinking that these cancel. The power has to be done first, and then you won't have 1/2 here anymore. You'll have something different. Now we have negative 1/2 times 1/2 to the x. This represents what's left after you've completed the vertical stretch by a factor of 6. Now we have to reflect it about the x-axis. An x-axis reflection means that if the graph was looking something like this, then it's going to change and look like this, where it gets reflected over the x-axis. To accomplish that, we multiply the front by a negative sign. This is going to lead us to the final form of our new equation, which I'll call g. G as a function is going to be a positive 2 times 1/2 raised to the x power. That's our new value. Now, if we're looking at this new value, the next question is, what is the y-intercept of the new value? Well, a y-intercept occurs when x is equal to 0. So to find that, I'm going to take part B, and I'm going to compute g of 0. That means I have 2 times the quantity 1/2 raised to the 0 power, which gives me, when I do the exponential first, anything to the 0 power except 0, which can't be raised to the 0 power, will give me the number 1. So this gives me 2 times 1, which is 2. So my answer to part B is 2. What is the domain? Well, the domain of my new function, 2 times 1/2 to the x, is going to be all reals. That's the standard domain for all exponential functions. So you can either write out all reals in words, or you can use interval notation. This depends largely on which professor you have. In interval notation, it's negative infinity to infinity. Make sure you have the negative infinity on the left, since it's smaller than the positive infinity on the right. Now the question is, what is the range? The range is all the values of y. Let's take a quick sketch of what the graph looks like so that we can see what it might look like. When we're looking at the sketch of the graph, what we're starting with, again, is our function g of x equal to 2 times 1/2 raised to the x power. I know that it's been stretched vertically by a factor of 2, which means that it's going to go through here at this value right there. So I have 1/2 raised to the x. Now, what's going to come next? Let's imagine plugging in a value for the x variable. Let's imagine plugging in a 1. 1/2 raised to the first power is 1/2, and 1/2 times 2 would be the number 1. That means that this will go through this point right here. Now let's imagine plugging in the number 2. 1/2 to the second power is 1/2 squared. 1/2 times itself is 1/4. 2 times 1/4 is 2/4, or 1/2. That means that the exponential function is falling as it comes over here. This is an example of exponential decay. Let's try using a -1 as our exponent. The -1 tells us to take the reciprocal of the 1/2, which makes it 2. 2 times 2 then makes it 4. This means that our graph is looking now more or less like this if we connect the dots. Remember that the domain is all the values that the x can be. If you were to pull all these values back to the x-axis, and remember it's continuing to slant outward, it would eventually cover up the whole x-axis. That's why our domain is all reals. On the other hand, if I were to imagine snow plowing all these points back on top of the y-axis, only the upper part of the y-axis would get covered up. No part of the graph goes below or even touches the x-axis. That means that the range, while it approaches 0, never touches 0. So I use a round parentheses on the left-hand side. Then it goes to infinity on the right. Since infinity is not a number, we'll definitely use round parentheses for that. Let's now look at problem 2. Problem 2 reads, the function f of x equal to 6 times the quantity 1/3 raised to the x power is shown in the graph below. Graph the reflection of f of x about the y-axis on the same axes and then give the y-intercept. So our graph is 6 times 1/3 to the x. Let's write this here at the top. 6 times 1/3 raised to the x power. This is our function f of x. What we want to do is reflect this function about the y-axis, which is this one. Imagine, if you will, that you put paint on top of this graph right here, and then you folded it with the y-axis as the crease. That means that the point 0, 6 would not move but would stay put. This point, however, would get reflected to here. That means that this point would get reflected to about here, and this point would be reflected to about there. That also means that since it's going through this point exactly, right there at 1, 2, I can reflect it and say that this one must be going through -1, 2. If you look down here, you can also reflect these by counting over 1 and a little more than a half, 1 and a little more than a half. And then you can draw the reflection as it comes down and approaches the x-axis from above. Notice that it never touches or crosses the x-axis. That's probably about the best I can do hand-drawn. The last question in this part was give the y-intercept. Notice that when you reflect across the y-axis, the y-intercept does not change because the crease of the page is on the y-axis. So the intercept stays the same at 0, 6. Now let's move to problem number 3. In problem number 3, we're to match the function with one of the graphs in the figure below. Let's make it smaller so we can see it all at the same time. Now that we can see the functions next to the graphs, let's choose the correct graph for each function. One of the first things to notice is that all of the coefficients are either 2 or 4. Why is that important? Well, when you think about it, if you allow the variable to be 0, then your exponential part will become a 1, and you will get that particular value as the y-intercept. That means that this first one has a y-intercept of 0, 2, as does this one, and this one, and this one. This one, however, will have a y-intercept of 0, 4 because it has a 4 on the front, and when anything's raised to the 0th power other than 0, we get the number 1, and 1 times 4 is 4. This means, looking at the picture, that this lower spot here must be 2, and this higher spot must be 4. That means, by process of elimination, that the only two possibilities for this second one and the sixth one are C and D. Now, which would be which? Now we look at the base. When the base is greater than 1, it's an exponential growth. When the base is less than 1 but greater than 0, it's exponential decay. That means that this one is decaying and this one is growing. So this one is a grow and this one is a decay. That means that I must have this one down here being C, and I must have the second one up here being D. Now let's take a look at the 4 remaining problems. They all go through 0, 2. Let's use which ones grow and which ones decay to help us separate. I have 2 that grow because I have 2 that have a base between 0 or greater than 1, rather, 1.6 and 1.31. That means that this one must be a growth exponential, and this one must also be a growth exponential. The only 2 possibilities are E and F, since A and B are both decay equations. To determine which one is which, let's compare the relative sizes. I've got 1.6 for one base and 1.31 for the other. 1.6 will grow much faster and get steeper much quicker. That means this one must be E. This becomes our graph. This second one doesn't grow quite as fast, but it is still a growth, and it is going through the point 0.2, so it must be F. Now let's look at the 2 decay. Notice that their bases are numbers between 0 and 1. When the number is between 0 and 1, it decays. Now what we want to do is look at the values of the base and compare them. On one of them, I've got 0.89, and on the other, I've got 0.65. This will tell us which one is decaying faster, if you will. Which one is getting lower faster? Which one is getting lower not as fast? It looks to me like the graph B is getting lower faster. If it's getting lower faster, that means that it must have the smaller of the values, and that means that this one must be B. It's the reciprocal of what we had up here. If we were to take the reciprocal, we would find that this would actually be the bigger number. So the smaller the fraction, the faster the decay. That means that the one with the base of 0.89 must be the one decaying not quite as quickly, which is A. That means that our solutions in order are E, D, F, A, B, and C. Remember that when it is growth and decay, you're looking for sort of opposite things. For growth, you're looking for the largest base to be the fastest growing, whereas with decay, you're looking for the smallest base to be the fastest decaying. Now let's look at the next problem, problem number 4. Problem number 4 is similar, so let's take a moment to get the functions up next to it. This particular question is asking which graph has the smallest value for A. Remember that the form of the equation looks like f of x equal to A times b raised to the x power. The x may have a constant multiplied by it, and it may be divided by a constant, but the x has to be in the numerator of the power. The next thing we want to ask is, what will make the A be the smallest possible? What effect would that have? We saw in the last problem that if we let the variable be 0, that made the exponential part become the number 1, and that provided us with the y-intercept. So for the smallest value of A, we're looking for the smallest y-intercept. The smallest y-intercept will be the one that's closest to the origin. In that case, we're looking for the graph that crosses the y-axis at the lowest point, which looks like it would be graph F. Let's move on now and look at the next problem. This says the function f of x equal 4 1/2 to the x is shown. Graph the reflection of f of x about the x-axis on the same axes, and then give the horizontal asymptote, the domain, and the range. Let's take a look now at what this is going to do for us. This is the graph of 4 times 1/2 time raised to the x power, and this is our f of x. We want to reflect this about the x-axis, and the effect that that has is it changes the coefficient at the beginning to be a negative. This becomes negative 4 1/2 raised to the x power. Now, what is that really going to do to our picture? When we're reflecting about the x-axis, we're basically taking a picture of this in paint and flipping it across the x-axis so that it makes an imprint down below. Let's take a look at what the imprint would look like. When we're looking at this one, we've got this graph right here, and this does not appear to be the correct graph. How do I know this? Oh, it is the correct graph. I didn't notice that the 1/2 is a fraction, and that does give us decay. So now what I want to do is I want to reflect it across the axis. Every point where it seems to go through exactly, I can multiply that by a negative, and that will give me the other value. So I've got 4 times 1/2 to the x. When I raise 1/2 to the negative 1, as in this point here, that takes the reciprocal and gives you 2. 2 times 4 gives you the 8. So on the reflection, we're going to have down here negative 1, negative 8, which will be the reflection across the x-axis. Let's find another point where it crosses through exactly. It looks like it crosses through exactly at 0, 4, which makes sense because when x is 0, the exponential part becomes the number 1, and 1 times 4 is 4. When we multiply by the negative, that will make it negative 4, and that means it goes through this point right here. The next point it looks like it goes through exactly is at 1, 2. If I allow the x variable to be the number 1, I get 1/2 to the first, which is 1/2. 1/2 times 4 is 2, and that gives me the point of 1, 2. Then I can reflect it across the x-axis and make it 1, negative 2. The next point that looks like it hits exactly is here at 2. Let's look at what happens when we let the variable be 2. 1/2 raised to the second power is 1/2 squared, which is 1/2 times 1/2, or 1/4. 1/4 multiplied by 4 gives us the number 1. That means that this ordered pair here is 2, 1. When we reflect it across the x, we get 2, -1. If we connect the dots and we have it approach the x-axis as an asymptote, then we get this graph right here. Now, as we're looking at this graph and we're trying to determine what will the domain and range be, what we're looking for in the horizontal asymptote, we're looking for what does it get close to but never touch or cross for the asymptote, all the values that x takes on for the domain, and all the values that y takes on for the range. Our horizontal asymptote is still going to be right here. It's still this y-axis. So when we're looking at that, what we have is the horizontal asymptote, which we'll write as HA. This horizontal asymptote is still here, and that is the line y equals 0. The next part is the domain. The domain are all the values that x can take on. Again, if we were to imagine all of these points being pushed back on top of the x-axis, eventually the whole axis would get covered up with solid paint. Even though this goes very rapidly down, it is still tilted outward, so eventually the whole x line would get covered up. This is all real numbers, or negative infinity to infinity. Be sure to give these in number line order. What about the range of this new graph? The range of the new graph is going to be all the values that y takes on. In this case, imagine pushing all of the values straight back on top of the y-axis. That means some get pushed to the right and some get pushed to the left. Notice that it never goes above the y-axis. So we have an upper limit of 0. It never touches it, so we make it round and not square. Does it cover up the bottom? Yes, it does, forever and ever. That means that we have a lower edge of negative infinity up to 0. Let's now move on and take a look at the next problem. This asks us to graph the transformation of 4 to the x, giving the horizontal asymptote, the domain, and the range. The transformation is 4 to the negative x. When you have 4 to the negative x, what's happened is you've reflected across the y-axis. Why the y and not the x? A reflection across the x-axis is shown by multiplying on the outside of the main operation, the exponential, by a negative. Having the other variable, the x variable, being multiplied by a negative inside the exponential reflects across the y. So this is reflected across the y-axis because x was multiplied by the -1. When we have this reflection, then, what we need to do is graph 4 to the x, and then we'll reflect it. In order to do that, I'm going to create a list of values using a table. I have 4 to the x, so I'm going to list my x values and my f of x values. I'm going to choose some positives and some negatives so I can get a good range. I'll start with -2, and then -1, and then 0, then 1, then 2. These are my favorite 5, but they may not all fit on the graph. When I allow x to be -2, 4 to the -2 is going to give me the reciprocal of 4 squared, which is a positive 1 over 16. That is a really, really low value. So that means that it is very low out here, must be getting close to the x-axis. What about when x is -1? that would give me 4 to the negative 1 value, which is the reciprocal of 4, or a positive 1/4. That means that it is 1/4 of the way up in there. So climbing, but not very fast. The next value that I'm going to be looking at is 4 to the 0th power. 4 to the 0th power is 1. That will graph here on the y-axis at height 1. 4 to the 1st is, of course, 4, and 4 squared is 16. 16 is too large for my graph, but I can graph 1/4 by graphing it there. Now I can connect these with a line or a curve that goes up very, very rapidly, and that decreases very rapidly as well. Now what we want to do is we want to imagine reflecting this across the y-axis. Let's change colors so that we can see it. Notice that when we reflect across the y-axis, which is what we get when we have a negative on the variable in the power, it will not change the y-intercept. So it still goes through that point right there. This point, however, which was at negative 1/4, will now be at positive 1/4. And this value at negative 2/116 will be at positive 2/116. The value at 1/4 will now be at negative 1/4. And this is enough to draw what it looks like as we reflect the shape across the y-axis. It is hard to get it to come low enough, fast enough without crossing the line. So take your time and make sure that you have a good graph. Next, we were asked to give the horizontal asymptote, the domain, and the range. For this particular one, when we're looking at the horizontal asymptote, it's the same as it was before. It's the x-axis, which is y equals 0. The next thing we want to take a look at is the domain. What will the domain be? That's all the values that x can take on. But again, the domain is going to be all reals just as it was before. It's taking on all values from the far left to the far right, though it will take a long time to push out to the right because it goes up so rapidly. The range has not changed either. In both graphs, I'm only going to be covering up from the origin above. I'm not going to cover up the origin though, because neither graph touches the x-axis. So the range value is going to go from 0 up to positive infinity. Let's now move on to the next problem. In the next problem, we're simply asked to select the graph of 4 to the x, and since we just did it, this should be no problem for us. 4 to the x is the black graph that we saw here. Note that it goes through 0, 1, and it also goes through the point 1, 4. That's what we're looking for, a growth equation going through those points. This does have the right y-intercept, but it doesn't go through 1, 4. So that's not it. What would the next one look like? For the next one, it's also going through 0, 1, which looks right, but it doesn't go through 1, 4, so that's not it. What is the problem going to look like? Let's take a look at the next one. The next one is going to be the one that is going through, let's see, 0, 1, and oh, so close, but no, it's going through 1, 5. You're not it either. This must be it, since this is probably the last choice. It goes through 0, 1, it goes through 1, 4, it goes through negative 1, 1/4, and negative 2, 1/16. This is the correct graph. Let's move on now. What is our horizontal asymptote, domain, and range? The horizontal asymptote is again the line that it gets close to but never touches or crosses. So our horizontal asymptote for this particular problem is again the x-axis, which is y equals 0. Our domain is all the values that x can take on eventually, no matter how long it takes to get there, and that will cover up the whole x-axis, so negative infinity to infinity. The y, however, nothing drops below the x-axis, so no negative values are used, and since it never touches the x-axis, it doesn't use the value of 0 either. That means that we start at open 0 and we go to infinity forever. Moving on to the next problem, it says select the graph of the transformation of 2 to the x. Give the horizontal asymptote, the domain, and the range. This is a graph that has been shifted up 2. That's all that's happened to this graph, is it was shifted up 2. That means that it should go through the points 0, 1, because when x is 0, 2 to the 0 is the number 1, and it should also go through the point 1, 2. When x is 1, it should go through 2. Let's take a look at these. Now, this is what 2 to the x goes through. What would it go through if we then shifted everything up 2? Instead of going through 0, 1, it would now go through 0, 3, since 1 plus 2 gives us 3. And instead of going through 1, 2, it would now go through 1, 4. So we're looking for something that crosses through at 0, 3 and 1, 4. Now let's take a look. Definitely not this guy. 0, 3, nope, that's crossing at 0, 4. 0, 3, yes, that checks. 1, 4, yes, that checks. This looks like it's probably it, but let's eliminate the last choice before we decide. Oh, definitely not. That means that this one must be our choice. What is the horizontal asymptote now? Notice that when you shifted it up, it changed the horizontal asymptote. Instead of being the x-axis, it's now the line y equal 2. So when you shift up or down, you're changing the horizontal asymptote up or down as well. What about the domain and the range? We haven't changed the domain. It's the same graph, so it stretches across the same x values. However, by shifting up or down, you do affect the range. Because we have shifted it up 2, I'm no longer even using the values between 0 and 2. And I don't use 2 either. So my range got shifted up 2 as well, from 2 to infinity. Let's take a look now at the next problem. The next problem is problem number 8. Looking at problem number 8, we're asked to graph the transformation of 4 to the x plus 2 power. Give the horizontal asymptote, the domain, and the range. You can always set up a table if you want to evaluate 4 to the x plus 2. Or you can think of this as g of x being 4 x minus a negative 2. This tells me that it actually went left 2. We can always use some points, though, to verify that it did. All right, remember, when you're adding and subtracting inside the exponential next to the x, that shifts it left or right, but opposite the direction you think it should go. Since it's a plus, you might think it goes right, but actually it goes left. And that's because the formula has a subtraction symbol in it. It's really x minus a negative 2. The negative 2 moves it left. So what is it going to look like? Well, it's the graph of 4 to the x. It's just been shifted left 2. Let's draw the graph of 4 to the x again, which hopefully you remember what it looks like. If not, you can scroll back up to check it out. It looks like this. Now we're going to take this graph and we're going to shift it to the left 2. That means this point here at negative 2, 1/16 goes to negative 1, 4, 1/16. The point at negative 1 1/4 shifts left 2 to negative 3 1/4. The point at 0 1 shifts left 2 to negative 2 1, and the point 1 4 shifts left 2 to negative 1 4. Then I draw the same picture, just picked up, shifted over to the left 2, and put that back down more or less like a sticker. Now we need to give the horizontal asymptote and the domain and the range. Can you see that in the picture, the horizontal asymptote has not been changed? Therefore, it's still the x-axis, which is the equation y equals 0. The domain has been shifted left, but because the graph stretches in both directions forever, the domain actually does not change and remains negative infinity to infinity. The range has not been changed either because it didn't shift the graph up or down. That means that our range is going to go from open 0 to positive infinity, just as it did previously. Now let's take a look at the next problem. In this problem, it says, start with the graph of f of x equal 3 to the x, then write a function that results from the given transformation. We want to shift the function 8 units up. Moving up or down happens outside the operation. It affects the y, which is not in the exponential. So that means that we simply write 3 to the x plus 8, and that will shift it up 8. How about the next problem? Start with the graph of f of x equal to 8 to the x, then write a function that results from the given transformation. Reflect f of x about the x-axis. Reflecting about the x-axis actually gives you a graph that comes over the x-axis and shows the reflection down below. In other words, it would reflect and go this way instead if it were a growth equation. This is a vertical change, and because it's a vertical change, it's also outside the operation. That means all we need to do is multiply the 8 to the x by a negative at the front. Let's now look at the next problem. In the next problem, the graph is a transformation of y equal 3 to the x. Write an equation that describes the transformation. Let's take a look and see what we've got. This is a transformation of 3 to the x. I know 3 to the x should be going through 0, 1, but it looks like it's going through the origin. That makes me wonder if maybe they've taken 3 to the x and subtracted 1. If that's true, then instead of going through 1, 3, it'll be going through 1, 2, and it certainly is. It also means that instead of going through negative 1, 1/3, the reciprocal of 3, it goes through negative 1. Sorry, I lost my track for a minute there. Negative 2/3. It gets reflected, which is correct. You can also check this one by going to 2, except that that one unfortunately is off the graph. It looks to me like the graph transformation is 3 to the x minus 1. In this problem, we want to evaluate the exponential function for the indicative value of x. Round your answer to 2 decimal places if necessary. I want to calculate f of 6. That means that I'm going to rewrite the problem and I'm going to open up a hole for where I used to have the variable x, and I'm going to put the 6 inside the hole. That will protect me from making an order of operations error. Remember to do the exponents first, so the 1/2 and the 2 as the base remain the same while I subtract 1 from 6 to get 5. Order of operations tells me exponentials first, so the 1/2 remains on the outside until I evaluate that 2 to the 5th is 32. Finally, I do the multiplication last. This gives me the number 16, which is our final value. Let's take a look now at the last problem, problem number 14. Looking at problem number 14, we are to evaluate the exponential function for the indicated value of x. Round our answer to 2 decimal places if necessary. This time we want to evaluate f of 1. Again, I rewrite the problem, opening up an empty set of parentheses for the variable x, and then I will dump the value I'm substituting into the hole. This means that I'm going to dump a 1 into the hole. The first thing has to be adding together the 1 and the 3 in the exponent. That gives me a 4. The next thing that has to happen by order of operations has to be the exponent. That happens before multiplication. 3 to the 4th gives me 81. Then I have 3 times 81 minus 1. Multiplication happens before subtraction, so I take 81 times 3, which is 243, minus 1, which finally gives me the final answer of 242. I hope that this video will help you to solve the problems in your homework on graphing exponential functions.